Hi guys, welcome to the Introduction to Clojure tutorial. My name is Tensor from the Tensor Programming blog. So today I thought we would take a little look at Clojure. Before that, however, I just wanted to make a few announcements. For those of you who are waiting for the next Elixir tutorials, those are on their way. They're just taking a little longer than I anticipated to actually write and to create. Also, those of you who are still watching this channel because you're interested in some of the other languages that we've looked at, like Elm or Go, don't worry, we will go back and visit those languages. Basically, I want to get a good base of languages onto this channel. So the next language that we want to enter into our channel here is Clojure. And we decided on Clojure through a poll on Twitter. I put up a poll between Clojure, Kotlin, F#, and Dart. And for a long period of that poll, Dart was actually winning by quite a lot. And then on the very last day, a bunch of people came in and voted for Clojure, and it ended up winning in a landslide. Clojure is a dynamically typed functional programming language that runs on the JVM. This of course allows it to provide interop with Java. One of the major design goals of Clojure was to make it easier to implement concurrent applications that can access large amounts of data. Clojure also has a build that runs on the .NET platform, so this means of course that it has interop with .NET. This is called Clojure CLR. Now this is a version that we probably won't touch on. There is also a version called Clojure Script, which has interop with JavaScript and compiles down to JavaScript. This version we definitely will look at later. Now, one of the very nice things about Clojure is that it's got a very small core, and this is mainly due to its heritage in Lisp. Clojure is a derivative of Lisp, and Lisp was a language that was created in 1958. It is the second oldest high-order programming language ever created, and Lisp stands for List Processor, and you'll actually see why here in a moment when we actually take a look at this code. The other thing I kind of want you guys to keep in mind as we're going through these functions is that Lisp and Clojure treats code as data. Now this sort of statement will become more and more pertinent as we continue on. Alright, so this tutorial is going to take sort of a different approach than what we did before. So before with Elm and with Go and with Elixir, we just opened up a REPL, we typed in a bunch of the different features of the programming languages, we talked about them for a little bit, then we started doing examples. In this instance, we're going to start by looking at examples. However, we're going to break these examples down and explain exactly how they're working. I feel like this is a better way to at least teach this language to you guys. Alright, so let's look at our first function. As you can see here, we have this function, and it is called factorial, and I'm sure you can kind of guess what it does. The first thing that you will probably notice are all the parentheses. Now this is something that is very common in Lisps and of course in Clojure. So Clojure uses what is called a prefix notation. Normal programming languages use a different style of notation. Typically with other programming languages, you have the function name first, then you have the arguments inside of a set of parentheses, and then you have the function body either in curly braces or through indentation. With Clojure, however, we take these parentheses and we extend them all the way to the front of the function name and to the end of the body, and we get rid of the curly braces and the indentation instead. So every single time you see the start of a parenthesis in Clojure, you can rest assured that the first statement is actually a function. That is actually true for this entire piece of code as well. This first statement here is a macro that allows us to create a function, and its arguments are the name of the function, which is this symbol here, a vector of the arguments of the function. In this case, we only have one argument, which is n, and then the actual function body itself. And by doing this, this actually creates a function, and as you can see here, this is the actual output of running this code here. And it tells us that this code created a factorial function on the namespace tutapp.core, which is the file that we're in. Now namespaces are like modules in other programming languages, and of course there are other programming languages that also use namespaces like C#. To read Clojure code, you always kind of want to look at the inner part of the code first, and then work your way outwards. So if we look at this inner part here, we have this function dec, and it is passing n through it, which is our argument up here. Now if we just pull this out of the code here and we write dec 10, you can see that it actually decrements the number that we've passed through it. That's exactly what this piece of code is doing. It's taking the argument and it's decrementing it. Then we also have a recursive call here. So this is actually calling the function inside of the function. Now ignoring this recursive call here, let's go to the next part. So the next part, we have this star, and then we have our argument, and of course we have our decremented argument here and the function call. So let's just pull out the star part and find out what's actually happening here. So the star actually means multiplication, and as you can see here, we can pass in two arguments, 10 and 9, and they multiply together and give us 90. So to find out what the factorial of dec n actually means, we kind of have to look at the rest of our function here, more specifically this if statement. So we have this if statement, and then we have this equals n1. So what does this equals n1 actually mean? If we type in equals 1, 2, we get back false. If we type in equals 1, 1, we get back true. So it's pretty apparent that this is just a Boolean statement, and it's basically saying if n equals 1, then we do this bit of code, which is return n. Otherwise, we run this rest of the function here. Alright, so now we're kind of getting somewhere. So what this basically is showing us is that when we put for n, it came through here first, and it came back as false, therefore this bit of code was removed. Then 4 was decremented here, so it became 3, and then 3 was passed back through the function again, so passed back through this if statement, which it returned false again, and it was multiplied by n. And of course, by being passed back through this if statement as well, it also created a decrement of 3, which became 2, which was then passed back through the function again. So our function actually created this pattern inside of it. We pass in 4, it decrements it to 3, it multiplies 4 times 3, but then again it passes 3 back through the function, which it then decrements to 2, and then it multiplies 4 times 3 times 2, passes in 2 again, which it then decrements to 1, and then 1 fulfills this if statement, and then it passes back n, which is 1, and then it multiplies all of these together and we get 24. And as you can see, if we call our factorial function again on 4, we do in fact get 24. Alright, so now let's look at something that's slightly more complicated. So this is a Fibonacci sequence function, and we're going to now just go over it real quickly. So first we have our defn macro, which is defining this function, and we're defining it as fib, and then we have one argument that's being passed into here, which is n. Then the next part of the function is the function body. However, this function actually is acting like a wrapper of sorts, because inside of it we have an anonymous function. So this fn is actually a macro to create an anonymous function, and then this next vector is actually our 4 arguments. So we're creating an anonymous function with 4 arguments, and then we are passing it down to this conditional statement, and then we are using this recur keyword to recursively loop through the actual anonymous function. Alright, so let's start with the inner part of our function, and that is this plus a and b. We're actually passing these numbers here as arguments to our anonymous function here. So 1 is equal to a, 1 is equal to b, 2 is equal to c, and then this vector here is equal to this sequence variable. So let's run fib of 7, and as you can see here, it returns a vector of the first 7 numbers of the Fibonacci sequence, 1, 1, 2, 3, 5, 8, and 13. So let's figure out how it actually got there. So first let's look at our conditional and talk about how this conditional actually works. So what a conditional is it's like a bunch of nested if statements. So our first if statement is asking whether or not n, which is the argument that the user is passing into the actual function, is equal to 1. And if it is equal to 1, so if this comes back as true, then we just produce a vector of 1. So if we were to call fib 1, it would just stop here and produce us a vector of 1. And that would be our answer. Otherwise, we come down here to the next part, we try to see if n is equal to c. Now in this case c is 2, so if we were to put 2 in here, this would actually just return 1, 1. You can see this by actually calling fib2. It's returning the sequence or the initial binding of seek back to the user. Then we have this little else keyword after this last conditional. And the way this else keyword works is it tells this conditional here, this function, that any other case we want to do this part of the function. So since we know about this part of the function, and since we know that 7 does not fulfill this part of the conditional or this part of the conditional, let's actually walk through this part of the function as we go up to 7. So in our initial loop through, a equals 1, b equals 1, c equals 2, and the sequence is 1, 1. Now if we look in here, we have a plus b, which would equal 2, and then we have this conj part. So we're calling conj on our vector, so 1, 1, and then on the result of this function, which is 2. Now if we actually call conj on 1, 1, and 2, we can see here that this is actually putting 2 into the end of our vector. So we're getting 1, 1, 2 as a vector. We are also running this incc piece of code. So what does this do? So we know c is 2, so if we run inc2, we get back 3. So this would return 3. So if we write this down, now we have 3, and we have this new sequence. Then for the next part, we're adding a and b together again. So 1 and 1, which is 2. And then we are just returning b, which in this case is just 1. So for our next loop through this recursion, a would equal 1, b would equal 2, c would equal 3, and this would be the sequence. So let's then go through the next loop. Now if we look, we are adding a and b together, which is 1 and 2, so we get 3. And then we're adding that to our sequence, which gives us back 1, 1, 2, 3. Then we're incrementing c, which takes 3 and gives us back 4. Then we're adding a and b together, which gives us 3 again. And then we're returning b, which is 2. So now a equals 2, b equals 3, c equals 4, and then this is our sequence. Because c is now equal to 4, this condition still hasn't been satisfied. So because we've passed 7 in, 4 is not equal to 7, so this recursion is going to continue. For our next loop through, as you can see here, a and b together gives us 5. We add 5 into our sequence. Then we increment c again, so that gives us 5 again. Then a and b together, which gives us another 5, and then b, which gives us 3. So now a is 3, b is 5, c is 5, and this is our sequence. Then, of course, for our next loop through, we now have c equals 6, so this condition still hasn't been met. A plus b, which is 3 plus 5, is going to give us 8. This is going to be inserted into our vector. Then c is going to be incremented again, so this is going to become 6, a plus b again, which is 8, and then we're going to get b back, which is 5. So now for our final loop, because we know that c is going to be incremented once more, going to become 7, which means it's going to be equal when it comes back through this conditional. Here is our final line of code, and as you can see, a plus b is 5 plus 8, which is 13. Then we pop that into our vector. Then we increment c, so that gives us 7, which is going to satisfy this condition here. Then we add a plus b here, which gives us 13, and then we return b, which is 8. So now a is 8, b is 13, c is 7, and then the sequence is this vector. This part of our conditional actually comes back as true. Therefore, we just return the sequence, which in this case is 1, 1, 2, 3, 5, 8, and 13. And as you can see, that was our answer for 7. So I hope you are able to understand how this function actually worked. This conditional statement is very handy, and it's something that you use quite a lot inside of Clojure. If you think about it, a lot of programs use nested if-else statements, and in this case, we can just combine if-else statements and make them less verbose and more compact. Also, this recur macro is very nice. It's optimized for tail-end recursion, which means that it works better on the CPU stack and allows us to deal with larger numbers and bigger pieces as a data. Alright, so here's the next example that we want to take a look at. As you can see here, we have this def, which allows us to create a global variable. So we're creating a global variable called val with a question mark, and we're assigning it to set AEIOU. So what does set AEIOU actually produce? Well, we can run it down here and see. So set AEIOU actually produces a collection called a set. The set starts with a number sign and a bunch of brackets. And with this set, we have each of our letters as a single element inside of this set. We then have a function definition right here. So this function is called pig Latin, and we are passing a single argument to this function. Now, if we come all the way down to the most inner part of our function, we have this subs word 1. So word is what we're passing down to our function. So this is the actual argument. So let's find out what this subs function actually does. So if we pass a string of hello to subs and then 1, we get back hello. So it removes the H from hello. So we can assume that subs actually removes the first letter of our word. So now we're kind of getting somewhere. So then for our next part, we have this str function, which is taking in hello. And then it's taking this first letter variable or function or whatever it is, as well as this AY string. So we don't know what first letter is quite yet, but we can find out if we look at this let binding. So what let allows us to do is bind a variable name, so in this case first letter, to a expression and have it be scoped to the block with which it was created. So in this case, our first letter is only scoped or only defined for this entire block here, and then outside of this parenthesis it doesn't exist anymore. So this is kind of nice, and it's actually better than defining a variable global sense in Clojure because it doesn't introduce as much state into our program. Our first letter is the first function applied to our word, which is our argument. So if we pass hello to first, we get \h back, which is our first letter. So this means that our first letter function here is actually just, quite literally, the first letter of the word that we're passing through this function. So then we can find out what this str function does. So if we pass in hello, and then the \h that we're getting from the first hello, and then the AY that was hard-coded in here, we get hello, hey. But what about the rest of this? So we have this if statement. What about this vowel first letter part? Well, this vowel first letter part, the way it's working is if the vowel has the first letter inside of it. So if we have A, E, I, O, or U as the first letter, then we're going to run this statement. Otherwise, we're going to run this statement. So in other words, if our word has a vowel, then we just concatenate AY to the end of the word. Otherwise, we remove the first letter of the word, and then we put the first letter of the word at the end of the word, and then we concatenate AY to the end of that word. So let's run our pig Latin. If we run pig Latin onto a word that has a consonant as its first letter, you can see that it actually takes the consonant and puts it at the end of the word and then adds AY to the end of the word. If we run pig Latin on a word that starts with a vowel, say A, like address, then all it does is concatenate AY to the end of our word here. So this makes sense with what we've worked through with this function. Alright guys, so that's the end of the tutorial. I hope you guys enjoyed this style of tutorial. If you have any questions or comments, any constructive criticism or anything like that, I would very much like to hear it. Whether or not you preferred this over the other style where we just kind of look at syntax. If you enjoyed this video, feel free to like and subscribe if you have any questions or comments, and of course feel free to leave them in the box below. And if you dislike this video, then by all means slam that dislike button as much as you want. I hope you guys have a good day.